It is through the process of homeostasis that animals are able to maintain a stable internal environment despite exposure to changing external environments. A homeostatic control system can regulate many different internal environments, one of them being body temperature, i.e. thermoregulation. Thermoregulation maintains the internal body temperature of animals within a certain range, even with a very different surrounding temperature. This control system is important in animals for many reasons, but especially so for the mammalian canid, the Arctic fox. Otherwise known as Vulpes aeagipus, these animals inhabit extremely cold climates, such as the Arctic tundra, Alaska, Canada, Russia, Norway, and Iceland. The Arctic fox has adapted itself physiologically, behaviorally, and morphologically for efficient thermoregulation in these sub-zero temperatures. Enzymes are more efficient at certain body temperatures, and so extreme ambient temperatures can often be very dangerous for the animals involved. If an environment is too cold, animals living in those conditions can be faced with extensive heat loss, which can slow down enzymes and molecules and reduce metabolic reaction rates, as well as potentially causing hypothermia. In some situations, the extreme cold can cause death, which eliminates the possibility for an organism to survive and reproduce. For these reasons, the Arctic fox must have efficient thermoregulation to avoid these problems and ensure the temperature of the blood going to the vital organs is constant, as well as the fact that as a mammal, enzyme activity halves for every 10 degrees centigrade drop in temperature without it. The homeostatic system of thermoregulation uses what is called negative feedback to maintain its set point at a constant value. In most mammals, the thermoregulatory center maintains a set point of 37.5 degrees Celsius, plus or minus 0.5 degrees Celsius. The negative feedback mechanism means that if a change occurs in the system, thermoregulation being temperature change, a corrective mechanism is triggered to reverse the original change and bring back the system to its set point. This means that the bigger the change, the bigger the corrective mechanism will be. The set level of this mechanism can never be perfectly maintained. Usually it oscillates either side of the set point, but can be more drastically altered in some situations, e.g. fever, where pyrogens are released by the white blood cells to increase the set point of the thermoregulatory center to help kill bacteria, which raises the body temperature by 2 to 3 degrees Celsius. This is considered a disruption to the homeostatic system. One important component of thermoregulation is the nervous system. The temperature control is located in the center of mammalian brains, in the hypothalamus. The hypothalamus helps maintain the set point of body temperature by using reflexes that enable vasoconstriction and shivering. This neural control does so through responding to chemicals from the body via input from its two sets of thermoreceptors. One set is found in the hypothalamus. This set of receptors is internal and help monitor the temperature of the blood as it passes through the brain. The other set of receptors are found in the skin. These can be used to monitor the external temperature, or the ambient temperature. Both sets of receptors allow the hypothalamus to control body temperature, e.g. bacterium that have been destroyed by phagocytic leukocytes, chemicals, called endogenous pyrogens, are released into the blood. The pyrogens then circulate to the hypothalamus to reset the thermostat, allowing the temperature of the body to increase or decrease when necessary, e.g. fever. Thermoregulatory adaptations in mammalian species differ depending on external environment. The Arctic fox has to endure extremely low temperatures and so has adaptations specifically suited to ensure efficient thermoregulation is carried out and internal body temperature does not become too low. Two of these thermoregulatory adaptations are morphological: body shape and fur. The body shape of the Arctic fox is round and compact. The body is small in size, as are the legs, ears, and muzzle. This helps retain heat internally as there is less surface area exposed to the cold external environment. The other major thermoregulatory morphological adaptation is fur. The Arctic fox has very deep, thick fur which is excellent for insulation. In sub-zero temperatures, it is able to maintain a consistent body temperature of around 40 degrees Celsius, while in Arctic temperatures as low as negative 50 degrees Celsius. This is because the thickness of the fur allows the Arctic fox to reduce heat loss. Looking at Figure 1, we can see the cross-section of the skin of a mammal slicing through a single hair. The root is embedded deep within the dermis, and when the erector muscles contract, the hair stands up, increasing internal insulation by trapping a layer of air within the fur. This insulative layer can become even larger during winter, when the Arctic fox's fur increases in thickness by up to 50%. Looking at Figure 2, we can also see the temperature gradient within the fox's fur. When exposed to an external temperature of negative 10 degrees Celsius, the tips of the fur are the same temperature, however the surface of the epidermis is close to 30 degrees Celsius. This temperature difference of around 40 degrees Celsius either side of the 6 cm thick fur layer can be attributed to the excellent insulating properties of the air trapped in the Arctic fox's long, fine, and densely packed fur, which help ensure the internal body temperature remains constant. The Arctic fox also has other physiological adaptations for efficient thermoregulation, another of the major ones being a countercurrent vascular heat exchange in its legs and paws, which help reduce heat loss. The legs of the Arctic fox are considered an extremity and are thinly insulated in comparison to the trunk of the body. To prevent major heat loss occurring here, the canid cools down its legs to around 0 degrees Celsius. Arterial blood in the legs passes in close contact with a network of small veins, and because arterial blood flows in an opposite direction to returning venous blood, heat can be exchanged very efficiently from the arteries to the veins. The countercurrent mechanism in the legs ensures that by the time the warm arterial blood flows into the legs and feet, it has transferred nearly all of its heat to veins returning blood to the body's core, ensuring little heat is lost from poorly insulated body extremities to the surrounding cool air. A consequence of this peripheral heat exchange, though, is that the legs of the Arctic fox must function at extremely low temperatures. The feet of the Arctic fox undergo a similar mechanism. There is a countercurrent heat exchange in the circulation of the paws to help maintain a stable body temperature and retain heat when walking on frozen ground. Also, to help maintain its foot temperature above tissue freezing point, -1 degree Celsius, while standing on an extremely cold substratum, there is an increased blood flow to a capillary route in the skin of the pads. Physiological adaptations aside, the Arctic fox has many behavioral adaptations for thermoregulation, one of these being snow dens. During cold weather, the Arctic fox will burrow under the snow cover to escape the harsh air and retain heat. This helps regulate the temperature gradient because snow is an excellent insulator and helps the fox avoid low temperatures above ground. When inside the snow den, the Arctic fox will curl up in a rounded position, further reducing the areas of its body exposed to ambient temperatures, creating a temperature gradient of roughly 52.5 degrees Celsius between the inside of the curl and the external environment. The position expands only the best insulated parts of the fox to help reduce heat loss. The fox curls up like a ball, hiding its poorly insulated head with a large bushy tail that acts as a warm cover. To enter the curled posture, the Arctic fox firstly lowers its lateral hip area onto the ground, bringing its hind legs forward and under its posterior trunk. The front legs are brought back along the inner side of the curl, formed by the ventral area of the torso. This is when the head is laid onto the forepaws and the tail is moved forward over the legs and muzzle, taking up half of its body length and completing the curl. The Arctic fox also undergoes seasonal changes, a behavioral attribute which alters morphological and physiological adaptations. In extremely cold climates, to adapt to low temperatures, the canid regulates thermal conductance, i.e. changing insulative properties of its fur and skin. One of the more recognizable seasonal changes is fur depth, with an estimated change of nearly 200%. In general, sites commonly in contact with the surface of the snow show substantial increases of fur depth and insulation during winter, e.g. foot pads. Parts of the fox that are not in contact with the snow's surface or exposed to the external environment, e.g. head, distal portion of legs, etc., show only minor seasonal changes and usually have less fur. The Arctic fox's skin also slightly decreases in temperature during the winter time, probably as a result of vasoconstriction of arterioles in the skin. This decrease in skin temperature is a result of a reduction in blood flow, which helps increase overall insulation to better retain heat. The Arctic fox inhabits extremely cold climates, which is why thermoregulation is so important. All mammals, including Vulpes arcopus, have a lower critical temperature. This is the minimum body temperature that can be tolerated by an organism. Below it, biochemical properties of cell structures, especially membranes and their permeability, are altered, slowing down chemical reactions within the body. For animals living in sub-zero conditions, there is also the risk of body water turning to ice. In some of these situations where the internal environment is altered, an organism is unable to maintain its usual bodily function as its chemical reactions are not occurring at a rate fast enough to sustain life. The Arctic fox's lower critical temperature is around negative 40 degrees Celsius, which is a temperature that can be reached by its external environment. It is therefore of utmost importance that it is able to maintain a stable internal environment and body temperature, despite an extremely cold external environment, to ensure there is no physical disruptions to cell structures and the Arctic fox is able to survive and reproduce.